All right, let's carry on this discussion on modern physics a little bit further. This video is going to be kind of a hodgepodge. I'm going to talk about momentum, this wave particle duality effect, uncertainty principle, electron diffraction, a bunch of different stuff. So each slide will kind of be its own standalone quandary. First, let's talk about Einstein's most famous equation, E equals mc squared. I'm not going to get into this in great detail in this video. This is going to come more into play when we get into the atomic physics side of modern physics. But ultimately, this equation comes from Einstein's theory of relativity, in which he describes all mass and energy as being equivalent. So if we know a quantity of mass of an object, we also know how much that mass is in energy form. And we know if we know the energy of material, we can kind of loosely describe how much matter should come out of this. If we were to explore particle physics, atomic physics, we'd be talking about things like binding energy, and particle physicists will be talking about this is how they can utilize the effect of atom smashers that figure out the constituent particles that get made up instantaneously. A bunch of stuff that we'll eventually get to, but not yet. Just understand the equation. E equals mc squared is true and holds true. It's going to come into play in one moment. Next, we know that a photon is able to move electrons. Photons come in, hit metals, they push electrons. That's the photoelectric effect. That one little thing is enough to show that photons, light itself, must carry momentum. It must have momentum. It's able to move an electron. Well, let's think about it. In the classical model of momentum, momentum is mass times velocity. In terms of light, because it's traveling at the speed of light, momentum is mass times c, or mc. But think about this. That implies that if a photon has momentum, it must also have mass. Well, it doesn't. Photons don't have mass. So something must be wrong with the classical model for momentum. And let's also take it one step further and recognize that Einstein also was able to show that a photon's energy is E equals hf. So what happens if I basically combine all of these equations? Now let's look at this guy here. P, momentum, equals mc. The problem here when we're talking about photons is this mass tidbit. Mass can't come into play here because photons don't have mass. So what I want to first do is I want to take these two equations, E equals mc squared and E equals hf, and set them equal to each other. So mc squared equals hf. Now I want to rearrange this for m to show that m equals hf over the speed of light squared. I'm going to take this whole thing and I'm going to plug it in for m over here. Momentum, therefore, will be hfc divided by c squared. Well, when I take one of these c's and get rid of this one, I get a new awesome equation. The momentum of anything can actually be related to Planck's constant times the frequency in which it's vibrating or moving divided by the speed of light. We will use this to help determine the momentum of individual photons. For example, as the frequency goes up, the momentum goes up. As the frequency goes down, the momentum goes down. Recognize that h and c, these are both constants if we're talking about light. We can, oops, Control Z, not Z. We can remove that C if we're talking about things that are not traveling at the speed of light and turn it into V. So we could use HF over V. Also, in terms of waves, V equals lambda F. Well, we could therefore replace V divided by F, or F divided by V, and inverse that to show that the momentum of a particle is h over lambda as well. So really these equations are all equal to each other and they all are describing the momentum of a photon. Alright, I'm going to come back to that momentum bit in a second, because recall we still have a little scenario here in the earlier 1800s where we have some conflicting physics. We have physics that shows pretty clearly that light will behave like a wave. That's the double slit experiment, diffraction, all of that stuff shows light behaves like a wave. But then we also have a very telling experiment that light will behave like a particle, and that's the photoelectric effect. So what the heck does that mean? What is light? Well, you might not like this answer, but it is true. We have to accept that light can behave as both a particle and a wave. And this is known as the particle-wave duality, or wave-particle duality, however you want to talk about it. But ultimately it says that really light can be described as particles traveling like waves, or waves that behave like particles. Whatever way you want to think about it, they're both accurate, and it gets way deeper than this. If we start to include all kinds of math, we can start talking about probabilities and when it'll behave like a particle and when it'll behave like a wave. And really, a greater period of the last 100 years of science have helped show a mathematical model on this. I'm not going to get into a whole lot of that, but I will, define it now. Light is both a particle and a wave. Well, think about this then. If light can behave like a particle and a wave, then maybe other particles can also behave like waves. And this guy named Louis de Broglie, and honestly his last name is de Broglie or something of that nature. Some people pronounce it de Broglie. I don't. It doesn't matter. Well, it does matter, and I apologize if he's listening in, which he's not. He will take it to the next level, and he's going to say that yes, it's true. Light is both particles and waves, and guess what? All matter will behave like waves. And what do you think, he's just randomly coming up with this? No. You know why he's able to come up with this thought? Well, we're going to put a pause on that thought until the next slide. But ultimately, he's right. All matter will behave like a wave. What? That's weird. That's like me saying if I throw a tennis ball through the air while it has momentum, it will be traveling like a wave. And if you pay attention to any other part of physics this whole entire year, we're talking about the linear model of physics here. A projectile traveling through the air, travels in a linear path. Of course, it'll get pulled down by gravity, so it'll have an ultimate parabolic path, but it follows linear physics. So how is it that this guy, Louis de Broglie, earns a Nobel Prize in 1923 for saying that, well, guess what? That tennis ball actually has a wavelength to it. Well, he's true. He's right. And I'm going to talk about that in a minute. But let's first remind ourselves momentum of something is equal to h over lambda. This is going to come into play on the next slide. So if every particle can act like a wave, then we must be able to actually see that in real life. We should be able to see something like a tennis ball traveling with a wavelength. Well, we do. We just don't see it with those really large objects because their wavelength ends up being insanely big. So you just can't notice it. But where do we actually notice it? We notice it with electrons. Understand, electrons are absolutely particles. They have mass. They act like particles, but it turns out that when you shoot a bunch of electrons through a double slit opening, a diffraction grating, any of that, you will get a diffraction pattern. That's weird. It made sense with photons. We can get into the Huygens principle about how it interferes and the two waves will cause interference patterns, but how on earth is it that electrons can indeed cause a diffraction pattern? I'm going to come back to all of this stuff in a second. Ultimately, what I am indeed saying is if I have a double slit opening and I shoot electrons at that opening, what anyone would normally say particles would do, they would say these particles would hit the wall right on the other side of the opening. They would travel forward just like any other particle. But, as you might expect, via experimentation, it turns out that these electrons don't actually land on the other side of that opening. Instead, you're probably going to know where I'm going with this. They create a maxima and minima pattern. We get evidence that electrons are showing up in a diffraction interference pattern, which shouldn't happen. Particles shouldn't do this. So then scientists will say, well, maybe these electrons created this pattern because as they were traveling to the screen, they interact with each other via the electrostatic force, and pushed each other that way. And sometimes they went here, and sometimes they had a greater repulsion force, and they made those maxima. And with enough times, these electrons are creating this pattern due to interacting with each other, right? So how do we remove that? What do you think scientists did? Instead of shooting one electron through the double slit at a time, or instead of shooting two at a time, they chose to shoot just one. So we have the one single electron, and you'd expect, well, of course, that one single electron must go forward, because even if it was a wave, how could it interfere with itself, right? Well, guess what? Yep, they created a diffraction pattern still. Even shooting them one at a time, we started getting electrons to show up in locations that you never would expect. And there's no way that they're interfering with other particles because they're only shooting one at a time. This does indeed imply that electrons travel as a wave and undergo that self-interference just like photons tend to do and create a diffraction pattern. So let's go back to this slide here and look at this graphic down here. So if when scientists send just one electron at a time, but up to say 40 total electrons, so again it was just one at a time, you start to get what appears to almost not be a pattern, and it almost looks like it's even scattering. But then we start to continue one at a time. Now we get even more electrons, say 200 electrons. And you start to see bands. You really do see these maxima. And then maybe 2,000 electrons, again, just one at a time. But now a total of 2,000, we're getting an even more clear idea where electrons will be found. And maybe we do 2 million electrons, and this gets tighter and tighter and tighter, are more prevalent. But you still see these outliers, right? You still see electrons toward the outer edges of these bands. And it shows that electrons, they're going to land in predictable areas, but we cannot predict precisely where. There's going to be a probability of finding an electron at a particular location versus knowing for sure exactly where that electron will go. And also recognize you don't know if the one electron will go to the left maxima or the right maxima or the central maxima. It's difficult to predict, but with enough data and enough collecting and analysis of mathematical models, we can start to get a probability of finding particles. And this actually is where the whole model of the electron model of the atom starts to expand. If you haven't taken chemistry yet, you'll learn about something called the cloud model or the Schrodinger model of the atom. If you have taken chemistry, you have an idea what I'm talking about. And this is whole idea about the probable location of electrons. And instead of the Bohr model where it says electrons exist in specific orbits, it says, okay, we have areas where electrons will more likely exist and areas where electrons will more likely exist. Regions of space and areas where we're likely not going to find electrons, so they have low probability there. And it starts to get very, very heavy in the probability world, which in the early 1900s and even still to this day, scientists didn't really like that. We liked the idea of knowing for sure where something is, where something's going, and where we can predict it to be. And quantum really opens up this whole window of saying, well, we don't know it's going to be here. It could be here, it could be there, and we start getting into probability distribution. And you start getting into some weird stuff, like the likelihood of an electron existing in more than one location at a time, or the fact that particles can apparently disappear or appear out of nowhere. And you start to get into all kinds of crazy stuff that I'm not going to expose you to right now, and I hope that if you're interested in this, that you explore. And the last one I do want to talk about is Heisenberg's uncertainty principle, which more or less is connected to this whole electron probability stuff. And it really it can be taken a lot deeper than this, so I'm not going to get into a very deep explanation of the uncertainty principle, but it asserts the fundamental limit to the precision with which the position and momentum of an electron can be known simultaneously. Really what this is we can have an idea where the electron is, but we'll never know its momentum, or we can have an idea on the electron's momentum, but you won't know its location. And this really has to do with this whole measurement bit. To be able to locate an electron, you have to hit it with something. Either you're hitting it with another electron or you're hitting it with a photon. But when you do that, there's a momentum exchange. So scientists will say, well, let's just hit it with one photon. Well, if you hit it with one photon, you don't have enough information to know exactly where it's going. So they say, okay, well, let's hit it with more photons. Well, you hit it with more photons, you have an idea where it's going, but now more photons, more momentum, you're now changing the actual path of the electron. So you will never really know for sure where an electron is. And this uncertainty principle is the foundation to quantum physics. And by the way, the whole concept of electron diffraction is not cuckoo. It happens. In fact, a scanning electron microscope is just that. Instead of using photons to look at stuff, we're using electrons to look at stuff because these electrons have a really tiny and understood wavelength, and we're able to go ahead and locate the object itself. And the last thing I want to do is just quickly do a little bit of math. I want to talk about that whole momentum is h over lambda, or more or less lambda, the wavelength of something, is h over momentum. And let's just look at a human being. Let's say their momentum is their mass times their velocity. So let's say it's a human being traveling, a 60-kilogram human being traveling or walking, say, 5 meters per second. What is their wavelength? Well, you would do 6.63 times 10 to the negative 34 joule seconds. Divide that by 60 kilograms times 5 meters per second, and you're going to get that person's wavelength. And it's a legitimate wavelength. That is indeed the wavelength of this person. Let me do some math right now on my calculator. We get a wavelength that is just insane. We're going to get 2.21 times 10 to the negative 36 meters. That's incredibly tiny. We can't detect that wavelength. That's well beyond the scope and limitation of the human ability to perceive or any tool to even measure. We can't come in anywhere close to measuring wavelengths that small. But now let's look at something like an electron. And we're going to do its mass, which is 9 point on average, or 9.11 times 10 to the negative 31 kilograms. And let's say it's traveling at speed near the speed of light. We'll say 2.7 times 10 to the 8 meters per second. And let's do some math here real quick. And we're going to get a wavelength that's a little bit more reasonable. It's still very tiny, 2.695 times 10 to the negative 12 meters. But this is now getting in a range in which we can measure. And this is what is often called the Fermi range, named after Enrico Fermi, which is also another famous mathematician and scientist that will be included in a later discussion. Okay, that's it for all of this stuff: momentum, wave-particle duality, electron diffraction, uncertainty principle, and etc. Thank you.